Hello everyone, greetings to all. Myself, Dr. Gowthaman, postdoctoral researcher, School of Engineering, Monash University, Malaysia. So my presentation topic is carbon quantum dots, an economical, sustainable Opto Electrocatalyst in sensing application. So I am from Monash University, Malaysia, and my basic research activities are based on the nanomaterials and metal organic frameworks based optoelectrochemical sensing and energy conversion and storage applications. So initially I started with the biometallic nanoparticles, then anisotropic nanostructures, then shifted to the low cost carbon nanomaterials and carbon metal nanocomposites with efficient activities and metal organic frameworks for optoelectrochemical sensing applications and energy conversion applications. So this presentation covers two parts. One is optochemical sensing of analytes based on carbon dots and graphene quantum dots based materials, and electrochemical applications of carbon dots towards the biomolecules, sensing of biomolecules. Okay, so basically carbon allotropes of carbon, they have different properties from graphite to diamond. Graphite is the softest, diamond is the hardest, and graphite is the lubricant and electrical conductor, whereas diamond is abrasive and electrically insulated. See, the both are from the carbon material, but their properties are in too extreme. So these are all from their peculiar properties. Like graphite have sp2 hybridization and diamond have sp3. The free electron of graphite leads to the electrical conductivity, and the sp3 hybridization leads to the electrical insulation of the diamond material. So, based on the carbon materials, we have two different properties, and a miniaturization of carbon material to the carbon nanomaterial leads to different peculiar properties, from carbon nanodiamond to nanofibers up to the carbon dots and graphene. So they have different properties based on their morphology and their um, physical properties. Application of carbon nanomaterials mainly utilized in different applications, from sensing to catalyst to um, drug delivery and all the system. The carbon nanomaterials were effectively utilized mainly due to their low cost, biocompatibility, abundant oxygen functional groups, tunable surface unit field properties, high surface area, and wide potential window. One of the important carbon nanomaterials is graphene. Graphene is a 2D sp2 hybridized material bonded with the carbon sheet and becomes a promising material for electrode fabrication due to its distinctive electrical conductivity and high surface area. Generally, graphene is synthesized from graphene oxide, which is synthesized from graphite by Hammers method. And graphite is oxidized to graphene oxide, and exfoliation of graphene oxide leads to exfoliated GO, and reduction of exfoliated GO leads to the graphene. Carbon nanotubes are other kind of carbon nanomaterials, which are the graphene layers rolled into a cylinder of tens of nanometers in diameter to form a hollow cylinders of carbon atoms. And different types of carbon nanotubes are available: single wall, double wall, and multi wall carbon nanotubes. The important property in the carbon nanomaterial is doping. Doping of the heteroatom, the nitrogen, sulfur, phosphorus into the carbon skeleton, leads to the change in their physical properties like electronic and electrical properties. And so especially the lone pair of nitrogen atom form a delocalized conjugate system with the sp2 hybridized carbon framework, which results in improvement in activity and electrical conductivity, leads to different electrocatalytic performance. Carbon dots are the other kind of material. They are the zero-dimensional carbon material that comprise discrete nanoparticles with diameters of approximately 10 nanometer. The GQDs are the other material. They are in the size of 100 nanometer. This is the major difference between the carbon dots and the graphene quantum dots. And the GQD exhibit stable photoluminescence, which are associated with the quantum confinement and edge effects. Similarly, the series also exhibited the highly fluorescent due to size and quantum confinement. The carbon based quantum dots classified into two, CDs and GQDs. CDs are crystalline and GQDs are amorphous in nature, and they can be synthesized from different carbon material like um, carbon rich material like carbohydrate, amino acid, and citric acid. So this kind of material can be utilized for the synthesis of the GQDs. The carbon material generally can be characterized by HRTM analysis for the morphological analysis, the cylindrical tube-like structures of carbon nanotubes, the um, sheet-like structure of graphene, and dot-like structure of carbon dots and graphene dots, and they can be characterized by XRD with the characteristic 002 band, um, 002 plane experienced at 26.4 um, 2 theta value, and the XP is also the important tool for the characterization of carbon nanomaterial. So here the CCCO C double bond O can be obtained from the deconvolution of C1s, and we can differentiate from the deconvolution. Especially the sp2 hybridization or sp3 hybridized carbon can be obtained at 284.4 electron volt to 280.4 84.6 electron volt, and the dominant highly oriented CC of unmodified single wall carbon nanotube exhibited the sp2 hybridization around 284.6. Similarly, Raman spectroscopy is another one important tool for the characteristic, the graphitization and defects analysis. The highly graphitized carbon nanomaterial can be characterized by the Raman spectroscopy. The highly graphitization leads to the large G band, and the defects leads to the D band. The 2D band is the double of 2D band, and we can so analyze the graphitization and the graphitization ratio from the G and D. So for the effective electrochemical sensor, the synthesis material must be attached on the electrode surface. The water electrochemical sensors, the devices that give information about the composition of a system in real time by coupling a chemically selective layer into an electrochemical transducer. The electrochemical sensors have more advantage because the electrodes can sense the material which are present within the host without doing any damage to the host system. And the electrochemical sensors can be classified by two. One is chemical sensor, another one is biosensor. The biosensor can be fabricated of the biomolecule and enzymes. The electroanalytical techniques used here is the cyclic voltammogram and the differential pulse voltammogram. From the cyclic voltammogram, we can get the information of the oxidation and reduction of the particular analyte, and which oxidation potential, what are the oxidation current, how the oxidation current or oxidation potential is improved. We can analyze, and from the differential pulse voltammogram, the oxidation or reduction of a particular analyte can be sensitively analyzed from the differential DPV analysis. So generally, we use the three electrode setup, working, reference, and counter setup for the electroanalytical. What are the principle of fluorescence? It is based on the Jablonski diagram. So absorption, fluorescence, phosphorescence. That is energy. The molecule absorb the photon, leads to the absorption from the ground state to excited state, and from the excited state to direct ground state leads to the fluorescence, and the excited state to triplet state leads to intersystem conversion, and triplet state to ground state the phosphorescence. Similarly, the luminescence also two kind of luminescence: relaxation from singlet excited state and relaxation from triplet excited state. There are two kind of luminescence are also. And what are the importance of biomolecules? The biomolecules like uric acid crystals are deposited in the joints, and it leads to gout disease. So the excess level of uric acid leads to gout disease, and excess level of glucose leads to diabetes. What are the lowest level? The lowest level of uric acid leads to the free moving of free radicals in the body, because the uric acid acts as a scavenger for the free radicals. So it can scavenge the free radicals, and it destroys the free radicals. So if the uric acid level is lowered, then the free radicals can be easily moved within our body, and it leads danger to our body. Similarly, the lower level of glucose lead to low pressure, and hence the monitoring the exact level of the biomolecules is highly important. Similarly, the pollutants also make humorous effect in our body by means of water or food or food materials, and hence we have to monitor the level of pollutants in the bodies. So the first part of this study is optochemical sensing of routine based on the carbon dots. So here the carbon dots can be synthesized from L-asparagine. So already I said the carbon dots or carbon materials can be synthesized from the carbon-rich source material. So here L-asparagine is taken as a source, and here the nitrogen also rich, and hence the nitrogen is doped by pyrolysis. So the pyrolysis of L-asparagine leads to nitrogen doped carbon dots. Lutein, also known as vitamin P, is a class of flavonoid that extensively found as an active constituent in leaves and fruits. Owing to its broad range of physiological functions, lutein is often used in Chinese traditional medicine. Taking lutein as a supplement is associated with some side effects due to ingestion of higher and more doses. So, as we discussed earlier, the luminescence is an important property. The figure A is the L-asparagine and B is for end of the series. The A does not show any luminescence, and B exhibited blue luminescence under UV light. Similarly, for the UV visible spectra of asparagine does not show any band, and the NCDs exhibited the shoulder peak around 340 nanometer, corresponding to the formation of NCDs, and the spherical dots leads to the formation of carbon dots, which is obtained from the HRDM analysis. And the carbon dots exhibited the uh, excitation independent emission, and the UV visible, sorry, the emission also observed around 480 nanometer with the intensity of uh, 400 intensity. So then the synthesized series can be characterized by XPS analysis. So the XPS analysis by deconversion of XPS survey spectrum confirms the presence of carbon, nitrogen, and oxygen in the series. The deconversion of C1S region giving the peak of CC, that means sp2 sp3 hybridization peaks, and CN, CO, C double bond O, C double bond N peaks, and a deconversion of N1S gives the primary, secondary, and tertiary amine groups, and the deconversion of O1S gives the C double bond O, COH, or COC bands in the particular electron volts. So the determination of routine by spectrophlorimetric technique here, as already we see the carbon dots, we have the intensity around 400, and after adding routine, the emission intensity is slightly quenched by each addition of 0.5 micromolar of routine. So after 15 micromolar of addition of routine, the emission intensity drastically quenched. This is due to fluorescence resonance energy mechanism, and this carbon dots is highly specific to the determination of routine among with the possible interferences such as Mg2 plus potassium, sodium ion, calcium, copper ion, and some amino acids and everything. So the second case is silver GQDs. GQDs is another kind of carbon quantum dots, and here silver GQDs are formed, and it can be utilized for the determination of. So initially GQDs are synthesized from the pyrolysis of citric acid. The incomplete carbonization leads to the GQDs, and um, complete carbonization leads to GO. This is according to the paper by Dong et al. In Carbon 2012. And after the GQD's formation, the GQDs is treated with the silver nitrate or by stirring, and there is a formation of silver GQDs. Here, the GQDs act as a autocatalyst to reduce silver nitrate to silver, and there is a formation of plenty of oxygen groups in the GQD surface, which leads to the fluorescence. So, The synthesized G codies and the silver G codies are characterized by UV visible spectroscopy. The UV visible spectra of G codies exhibited a peak around 360 nanometer, and after forming the silver nanoparticles, there is a formation of new band around 400 nanometers, characteristic to SPR, surface plasma resonance of silver nanoparticles. And the silver G codies exhibited blue luminescence, and after forming the silver nanoparticles, the luminescence is quenched. So because the surface of G codies is covered by the silver nanoparticles, and there is a and there is the quenching in the luminescence. The silver G codies are characterized by HRTM analysis, and the spherical particles with the average size of 9 nanometer is observed in the HR analysis. So the synthesized silver liquids is utilized for the determination of protamine. In order to avoid bleeding risk of heparin drug surgery, protamine acts as an antidote for heparin. Protamine readily binds with heparin electrostatically and reverses the anticoagulant activity. Overdose of protamine induces adverse effects which include hypertension, a sudden fall in blood pressure, male infertility, and cardiac arrest. And hence, determination of protamine is highly necessary in this field. So we take protamine. So here the AgGQD is a yellow color solution. Protamine is a colorless solution. The colorless protamine is added into the yellow color AgGQD. The color of the solution is changed to wine red color, and there is a complex formation between AgGQDs and so here, the UV visible absorption spectrum of AgGQDs is around 400 nanometer. Already we discussed. After adding protamine into the solution with a different concentration from 0.02 to zero point 0.3 microgram, the absorption band is drastically quenched, and also there is a new band is arised around say 560 nanometer. This is leads to the change in the morphology of the silver nanoparticles, and there is a complexation between the protamine and the AgGQDs. Hence, the color of the solution is not aggregated, and the color of the solution leads to color yellow color to violet color. So the AgGQDs are completely aggregated. So this is for AgGQDs. This is after protamine added, and this is the aggregated structure, and hence the size of the nanoparticle is increased from 9 nanometer to 15 nanometer. It is evidenced from analysis, and the emission intensity also decreased after the addition of certain protamine, and after that the emission intensity is drastically increased because after certain addition the silver nanoparticles is binded with the protamine, and there is a complexation. So after that the silver nanoparticles are free from the GQD surface, and hence excess concentration of protamine leads to the GQD surface free, and hence the um, emission is retained. So here the selective determination of protamine. The protamine is the synthesized AgGQDs is highly selective towards the determination of protamine with the other possible interference. Okay, the second major part of this study is the electrochemical sensing of biomolecules using carbon-based materials. So for the effective electrochemical sensing, we need to fabricate the synthesized carbon materials on the electrode surfaces. The first case is attachment of the carbon material using the linker. Here we take 1,6-hexadiamine. The 1,6-hexadiamine, the amine terminal is attached into the carbon via the like nucleophilic addition and Michaelis like nucleophilic addition, and then the free amine is utilized for the attachment of GO, and then the electrochemical reduction leads to the formation of graphene. Similarly, the melamine is grafted on the electrode surface with the help of HCl and sodium nitrate, and the free amines from the melamine are utilized for the attachment of GO followed by the electrochemical reduction of graphene. So the third part is the direct immersion. Actually, the amine group from the nitrogen-rich carbon material is utilized for the effective attachment via the direct immersion technique, and with the help of coupling agent, DCC coupling agent, and with the help of potential dynamic method and the drop cast method. These are all the method utilized for the fabrication of electrons. Okay, so here we have taken the nitrogen doped carbon dots synthesized from L asparagine, and we directly attach it on the electrode surface for the effective sensing of uric acid, tyrosine, and allopin. So here already discussed about the characterization of series with UV, etc. And we directly go for the electrochemical sensing applications. And this is electrochemical oxidation of uric acid. A is at the bare electrode, B is at the nitrogen doped carbon dots fabricated electrode. So when compared to the bare electrode, the nitrogen doped carbon, the NCDs fabricated electrode exhibited higher electrocatalytic activity towards the oxidation of uric acid, and we can detect the uric acid with the minimum concentration from 10 to different concentration, each additional 10 micromolar. We can detect the uric acid. Similarly, we can detect uric acid along with tyrosine and allopinol in a mixture. We can detect simultaneously all these analytes the help of the endoped carbon dots fabricated electron. Why we need to detect the uric acid along with tyrosine and allopinol? So generally, allopinol is the uric acid lowering therapy. So when the uric acid level excess for the gout patients, uh, the physician suggested the allopurinol for the uric acid lowering therapy. Okay, so the excess of allopurinol leads to the lowering level of uric acid. So what happens when the uric acid level lowers? When the uric acid level lowers, it cannot act as a scavenger for the free radical. So tyrosine easily releases the free radicals in our body, and the uric acid can scavenge the free radicals. So we can tyrosine at a higher level leads to the free radicals. So we need to detect uric acid, tyrosine, and allopurinol. We need to maintain the level of fluids in our body. So we take this specific study at nitrogen doped carbon dots fabricated electrodes. Fabrication of nitrogen doped carbon dots by potential dynamic method. So here we just the last case we direct immersion. In this case, we just deposit the carbon dots by potential dynamic deposition method. So here we just deposit the material with the cycling potential of minus 0.2 to plus 1.4 volt in 0.1 molar sulfuric acid, and dots were attached on the electrode surface, which is evidence from the SEM and AFM. And the electrocatalytic activity is analyzed from by analyzing uric acid, ascorbic acid, xanthine, hypoxanthine, and caffeine. So here, for simultaneously, we analyze 5 analyte in a single. So the end-doped carbon dots fabricated electrode is highly effective for the analysis of ascorbic acid, uric acid, xanthine, hypoxanthine, and caffeine. And so generally the hypoxanthine, xanthine, and uric acid are in the purine metabolism, and uric acid is the final product, and caffeine, ascorbic acid, they are all from the supplements we have taken. So we have to maintain the level of these 5 analytes, and this is for the first time we get the signals for ascorbic acid, uric acid, xanthine, hypoxanthine, and caffeine. So as conclusion, the basic studies on carbon nanomaterials we have discussed, and sensitive optical sensing of routine and protein based on carbon dots and GQDs, and electrochemical sensing the purine metabolites, and uric acid, tyrosine, and allopinol. We have discussed it clearly. So surely these strategies followed here could open promising new avenues for designing novel functional materials for clinical applications. So I express my sincere thanks um, to my professor, and also I would like to dedicate this presentation and this award, best researcher award, to the memory of my professor, research supervisor, Professor S. Abraham John, and his research group, Professor J. Jinshim from South Korea, Professor Janet Lim Hong Ni from University Putra, Malaysia, Dr. Y. C. Chang, my current supervisor. So I also I express my sincere thanks to all of them, and also I would like to express my sincere thanks to the funding agencies from Gandhidham University, UGC, DPT from India, University Putra, Malaysia, NM University, and Monash University. Also, I would like to express my sincere thanks to the uh, organizing committee and the panel members of the International Research Excellence and Best Paper Awards. Thank you.